Welcome to this lecture on the geologic timescale. Right, so during this approximately half hour, we'll cover how we've dated the Earth and divided up geologic time and how that has evolved over the years to our present day timescale. We'll then go over what the geologic timescale is as of 2021 and talk about the most recent epoch that we inhabit, which is the Holocene. So we'll start out with the recognition that time was very vast. This is something that has been known throughout different iterations, but in terms of geology, it was kind of first conceptualized with William Smith's 1815 map of England, which is one of the first geologic maps that we know of, at least in terms of the Western world. And this map just showed all of the rock layers that underlaid most of England, and through doing so showed that there must have been a lot of time. So each of these rock layers is angled, and through that angling spans kilometers and kilometers of history. And so this brought the idea that there must be a long period of time in which rocks have been forming, and that this period of time, in order to talk about it more efficiently, should be divided up into smaller subsections. Now we can actually calculate this rather than just looking at how many layers of rocks there are. We can use techniques like absolute dating in order to figure out the true age of the Earth. So if you want to read more about absolute dating, there's this great Scientific American article, How Science Figured Out the Age of the World. But I'll go over the main points here. So we know that the world right now is about 4.54 billion years old. We've calculated this based on a technique called radiometric dating, which relies on the radioactive decay of one element into another. So we'll go over quickly what radiometric dating is and what rocks it is applied to in order to figure out the age of the Earth. So radiometric dating you may be familiar with in terms of radiocarbon dating, for example. And it essentially takes advantage of the half-life decay of isotopes. So you know that isotopes like uranium-238 will decay into a new isotope of lead-206 over a period of 4.47 billion years. So over that 4.47 billion years, half of the uranium-238 will become lead-206. Another isotope of uranium, uranium-235, has a half-life of 710 million years, and it decays into lead-207. So these two uranium systems allow us to date things that are really old because their half-lives span 4.47 billion years and 710 million years. So an example of how this works is we have this original mineral here that's outlined in gray, and this mineral contains some uranium-235. After one half-life, of those 8 uranium-235 atoms, half of them have now become lead-207. And so if we were to pick up this rock as it exists in this middle figure, we could measure the relative amount of lead-207 to uranium-235 and calculate that about 710 million years must have passed one half-life. If we were to pick up this rock and we'd find of the 8 atoms within it, 2 are uranium-235 and 6 are lead-207, we can ask ourselves how much time has passed. We can back calculate that one half-life led to 4 and 4. Another half-life would take these 4 uranium-235 molecules and transform them into lead-207, or they would decay to lead-207. And so that would leave behind 2 uranium-235s and a total of 6 lead-207s. And that's exactly what we have in this diagram on the lower right. So this tells us that 2 half-lives have passed, and therefore this rock is approximately 710 million years times 2, or 1.42 billion years. Billion is abbreviated by a capital G. and A stands for years or annum. So this method of radiometric dating has been used to date the age of the Earth because we can, using the uranium-238 system, we only need about 1 half-life to get to the age of the Earth. Using the uranium-235 system, we would need about 6 to 7 half-lives to get to the age of the Earth. So this allows us to look at a variety of rocks, measure the uranium, and figure out how old they are. However, the question becomes, what rocks do we use? Unfortunately, it looks like this GIF is not going to work, but if we look at the Earth through time, because of plate tectonics, we are constantly moving continents around, we're constantly subducting material. And so the rocks that are present on Earth's surface are not very stable. They have been recycled through the process of the rock cycle and plate tectonics. We do have some areas in the middle of continents where we can find some really old rocks that have avoided being subducted. These tend to be in Canada, Greenland, and Australia, where we have rocks that are about 4 billion years old or younger. However, this is still younger than our current estimate of the age of the Earth. And so we can't actually use Earth rocks to get the age of the Earth. Instead, we turn to using rocks from elsewhere in the solar system. So for example, we have used the uranium series to date moon rocks. Because the moon has no tectonics, the rocks on it are not subject to this constant recycling and overturning. And so we can date these rocks to get an estimate of how old the moon is. The moon is actually formed from the original Earth. At some point in Earth's history, a large impact with the proto-Earth caused part of the Earth to actually detach, and that forms the current moon. And so the moon rocks are pretty intimately linked to the formation of Earth. These rocks have been dated between 4.4 to 4.5 billion years. We've also dated meteorites. Most of these meteorites were formed during that same kind of Big Bang and formation of the solar system that eventually formed our Earth. And so by dating these meteorites, we can get another proxy for the age of the Earth's formation. And these date to about 4.53 to 4.58 billion years ago. So with these two ages, we can approximate that the Earth's age must be very similar. And so that's how we usually get our estimate of about 4.5 to 4.6 billion years. This is quite a lot of time to think about and often is very hard to visualize. So I think this YouTube video, which was put together by NPR, is a really great way to visualize geologic time by making an analogy to a football field. So I will link this on our Canvas page so you can watch it on your own. Another way to visualize this has been this Twitter account called Year on Earth, and every single year it starts over again and basically compresses all of Earth's 4.54 billion years into 1 year on Earth, and then just kind of tweets when events would actually occur on that timeline. And that Twitter account will be very, very empty until about December, when most of the Earth's history as we know it and recognize it occurs, which you can see is like on the football field near the end zone of the present time is where we start to see a lot of activity. Okay, so 4.54 billion years is quite a lot to talk about. And so it is useful to start to divide this time into geologic steps. And so this gets us into the geologic timescale and how we've developed this. Currently, we divide up geologic time with these set boundaries called Global Boundary Stratotype Section and Points, GSSPs, or more informally, they're known as golden spikes. These actually look like golden spikes. You can see the spike that represents the boundary of the Ediacaran. And these are just put into rocks that were formed at the boundary between different geologic times. But how did we decide to do this? And how did we decide that these rocks were the boundaries between time? Well, that leads us through a history that started in the 1700s. So in the 1700s, as we started to get a better idea of all of the rocks around Europe and other kind of central places, geologists started to group time by the rock type. This was called geognosy. Arduino sort of pioneered this in the 1760s, and he classified mountain-forming rocks as either primary, secondary, or tertiary based on their proximity to the central mountain range. These words have actually kind of trickled through, and so even though we don't use primitive or secondary anymore, we do still use tertiary. This was in the geologic timescale up until a few years ago when it was replaced by the Neogene and Paleogene. However, you still see references to tertiary showing up in geologic maps, and that relates back to this original geognosy classification. So to give an example of how geognosy could be used, we'll take a look at the rocks near Colorado Springs. So we are here at Colorado College. And if we take a very basic geologic map of the rocks around us, we go very generally from close to the mountain front, a limestone, then to a sandstone, then to clastic rocks. So this would be a sedimentary rock of somewhere kind of similar to a sandstone, perhaps, and then to a shale as we get out into the plains. And we could use these rocks in a geognosy style interpretation to go through the rock history, with the limestones being the oldest and the shales being the youngest. And these basically record a shift in the paleo environments here. We start out with this limestone that formed in a marine environment, move to a sandstone that is reminiscent of beaches and dunes, to a clastic, which is a somewhat vague term that essentially means it was formed somewhere on land, and then to a shale, which must have formed in a very quiet environment because it's made of clay-sized particles, and that would be more reminiscent of a lake or an ocean. And so we could use the order of these rocks to say that we must have changed paleo environments from being underwater to on land to being back in water. This would record sea level changes through time. And this progression makes sense. However, if we scaled out to a much larger view, the whole state of Colorado, for example, and we still have the rock units colored by the type of rock that they are, it is no longer so easy to create this linear geologic story from the rocks. And so here geognosy kind of starts to fall apart as you get into more complicated geologic histories and to rocks that formed multiple times through that geologic history. So this indicates that rather than just using the type of rock, we also need an element of time, which makes sense for our time scale. And the earliest sense of time were fossil assemblages. So in the 1800s, we started to group rock types into different ages based on the fossils that we would find within those rocks. We call these fossil assemblages. Over time, the frequency of fossils and the abundance of different fossil types will change. And we can use this abundancy, frequency, as well as the different types of fossils to create assemblages that mark out geologic time. And in particular, we can mark out mass extinctions. So in this 1860 division of time that's shown in the lower left here, we're looking at the fossil abundance on the x-axis or y-axis and time on the x-axis. And you can see how the fossil abundance reaches a minimum a few times. And these might be during periods which are now known as mass extinctions. These created a very easy way and convenient way to divide up geologic time. Whenever we found these minimum in fossil assemblages, we could break this up. So in this instance, we broke time up into the Cenozoic, Mesozoic, and Paleozoic. And these still exist today. So we still use these terms. We're currently in the Cenozoic. The Mesozoic was known as the age of the dinosaurs. So this decrease in fossil abundance between the Cenozoic and the Mesozoic would have been that asteroid impact that killed off the dinosaurs. On the upper end of the Mesozoic is the boundary between Mesozoic and Paleozoic, and this would have been the end Permian extinction, which killed off almost 90% of life. So for a while, this was used to demarcate time. However, once you wanted to get into smaller divisions of time, it became a little bit more difficult. For instance, within the Cenozoic, we have a fairly abundant fossil assemblages, or fairly abundant fossil life. And so how do we divide things up further within this 65 million years, which is the Cenozoic? And we also need some way to divide up time that maybe isn't so dependent on mass extinctions or biotic changes. This original use of fossil records has created a bias so that our geologic timescale as it is today is very much weighted on fossil changes. You'll often see that at time boundaries, there's also a large fossil change. But we needed to go further than this in order to divide up time even more into manageable chunks. And so this brought us in the 1950s to the use of global boundary stratotype section endpoints, or GSSPs. These are much more standardized than the previous divisions of time, and it's formalized by a standing committee. So these GSSPs represent a standard global time stage that is not always at a fossil break. So one benefit of using GSSPs is the recognition that fossil breaks may not always occur at time breaks, and time breaks may not always have to occur at fossil breaks. So it allows us to separate those two a little bit more. And it also develops these type localities. So every time there is a division in time, there is a location on Earth that records that division in time in which we can reference back in order to see what those changes are that bound the time periods. Right. So these GSSPs are going to define the bottom of a time interval called a stage. So for example, of this rock arch, the rocks within it represented one time interval. The oldest rocks would be on the bottom, which we know from the principle of superposition, and the younger rocks would be on top. The GSSP for this time period would be present at the bottom. So it would represent the start of this time at the oldest rock and go up towards the youngest rock, at which point there may be another GSSP for the next time period. These GSSPs are very formalized, and so they have to be approved by the International Commission on Stratigraphy. They need to be correlatable over a wide area. They need to contain secondary signals or proxies to support that correlation. So rather than relying on one signal, like one change in fossil assemblages, there should be multiple signals within this defined GSSP. Those could be chemical signals, for instance, a change in oxygen abundance. In order for this to be used by a wide variety of people, it needs to be in a location that is free to access. So we actually have one close by at the Pueblo Reservoir. And so that's a location that is publicly accessible. And then it also needs to be in a region where we had continuous sedimentation. So there is no break in time and no unconformity of any sort at that location. So this gave us the geologic time divisions that we have today. Starting from the largest, we have what are called super eons. There's really only two of these. So the Precambrian is probably the best known super eon, and that covers there's 3 eons before the current eon that we're in, and the Precambrian super eon encompasses those. Below super eons are eons, like the Hadean, eras like the Mesozoic, Cenozoic, and Paleozoic, periods like the Jurassic and the Cretaceous, and then epochs, which subdivide periods into things like the Oligocene and the Miocene. And then epochs are further subdivided into ages. So we are currently In the Phanerozoic eon, in the Cenozoic era, the Quaternary period, and the Holocene epoch. The Holocene epoch is not formally divided into ages, at least that we often reference. And so for our current time period, we often ignore the age subdivision. So this is the current time scale, up to date as of, I believe, 2019. And so you can see the Precambrian super eon, and then the Cenozoic, Mesozoic, and Paleozoic, which all belong to the Phanerozoic eon. We've got the Mesozoic, where we had dinosaurs, the age of dinosaurs, the Cenozoic, which has been really the rise of mammals, and the Paleozoic, which contained a lot of marine life, dominantly marine life. Not all of these are subdivided into equal age intervals. So if you note, the age is very small on the furthest left of each of these columns. The Precambrian goes until 540 million years ago. So most of geologic time is taken up within the Precambrian. Since plate tectonics has destroyed a lot of the rocks from this era or from the super eon, we don't have a lot of time divisions within the Precambrian. There's also less life, and so less obvious ways to subdivide the Precambrian super eon into different epochs. So your homework today will be to find a way to memorize the periods of the Paleozoic, Mesozoic, and Cenozoic. We'll come back to that in a little bit. Right now, we'll talk about our current epoch, which is the Holocene. The Holocene started about 11.7 thousand years ago, and it's known for being a period of interglacial activity. It is not the only interglacial in Earth's history, but it happens to be the current interglacial, which has been dominated by the rise of humans and of human-dominated activities. As I mentioned, it started about 11.7 thousand years ago, but is defined as being 10,000 years ago in carbon years before present. So radiocarbon is another form of radioactive decay dating, like the uranium series we just talked about, and it uses the decay of carbon-14 to nitrogen-14. This occurs over about 5,000 years, and so radiocarbon dating is really only useful over the last 50,000 years. And it can be used on things like wood, shells, and charcoal. However, this radiocarbon dating and radioactive decay will translate into what's called carbon-14 years before present. If we measure the ratio of carbon-14 to nitrogen-14, we end up with a date that is carbon-14 years before present, and which can be calibrated to the actual years before present. However, this calibration isn't exactly 1-to-1, and so that's how we end up with this mismatch between 10,000 years in carbon-14 years before present and 11.7 thousand years in actual years before present. And these diagrams on the bottom just kind of show that mismatch. So particularly the lower right here, this light blue line would be a perfect 1-to-1 match between the calendar age and the radiocarbon age. And you can see that for really past a couple thousand years ago, the radiocarbon age tends to be a bit younger than the calendar age actually is. All right, so since the Holocene is really defined by being an interglacial, it's important to talk about what glacial cycles are and how they're caused. So glacial cycles on a very kind of generalized scale are formed through variations in the Earth's orbit that have brought the Earth closer and further away from the sun. This results in changes in what's called insolation, and that results in a temperature change. So when we're farther away from the sun, we have less insolation and we have cooler temperatures. This leads to a glacial cycle. However, as the Earth's natural orbital variations bring us back closer to the sun, that glacial period will then transition to being a warm period or an interglacial. There's three main orbital changes that affect glacial cycles. The first is eccentricity, which has to do with the shape of our orbit, where it can range from being a circular orbit, in which case we maintain a similar distance away from the sun, or an elliptical orbit, in which case we get further and closer away from the sun. These eccentricity changes occur on timescales of about 100,000 years. And superprinted on that are the obliquity changes. And that has to do with what the tilt of the Earth's axis is. So we are not standing perfectly upright on the Earth. Instead, we wobble a little bit on our axial tilt. And that axial tilt is going to change on timescales of about, say, 50,000 years or 44,000 years, I believe is what's more exact. And then finally, on top of that is the precession. And so that has to do with what is kind of the wobble of both our axis and of our orbit around the sun. And that wobble occurs on a much shorter time scale of about 10 to 20,000 years. So these three, acting together, eccentricity, obliquity, and precession, control how much insolation the Earth is receiving, and therefore control whether or not we're in a warm cycle or a cold cycle, and whether we're in an interglacial or a glacial period. And these taken together are called the Milankovitch cycles. So ignore that. So what this does is these changes in insolation will affect what the temperature is, and that has an effect on how much precipitation the Earth is receiving, or a particular location on the Earth is receiving. In doing so, this changes the oxygen isotopes that are recorded. And we can look back at ice cores and at other coral records, anything that kind of takes up oxygen from the atmosphere or from the ocean, and we can look at how those oxygen isotope abundances have changed over time to relate back what the precipitation and temperature conditions were. So this means we can record glacial cycles in oxygen isotopes and use these as a record to look at past changes in glacials and interglacials. So that's what this graph here is showing. On the right, we're looking at thousands of years before present. The arrow I just drew points towards present. And as we go back through time, the global temperatures, which in this case, Lisicki and Ramo kind of extracted out of the oxygen isotopes, those temperatures are shown in the dark blue wiggles here. And you can see how those temperatures right now are fairly high as we're in the Holocene interglacial. They were low for a while in this glacial period, which is also called stage 2, marine isotope stage 2. And before that, they were in another interglacial, glacial, interglacial, glacial, interglacial. So we have these cycles occurring throughout time. In particular, these cycles occur throughout the Quaternary. The Quaternary is often kind of known as the time in which we had worldwide glaciations. Right, so the Quaternary, again, includes the Holocene epoch, and it also includes the Pleistocene epoch, which was right before the Holocene, and it's sort of unofficially defined by these repeated glacial cycles. These glacial cycles began about 2.58 million years ago. Originally, these glacial periods were about 41,000 years apart, so mainly controlled by changes to obliquity. But at about the mid-Pleistocene, those slowed down to be about 100,000 years apart. So now they're controlled more by the eccentricity of the Earth's orbit. While the Quaternary and the Pleistocene may be defined by having these global glacial cycles, we know that before then, there were actually other large ice ages. And in particular, there were these large events called snowball or slushfall Earth, in which the Earth became covered in ice or sea ice or slush, particularly closer to the equators. These are really interesting time periods to think about because we know that life existed throughout these snowball Earths. And so it's kind of an open question of how life survived in these conditions. And that may help us think about how life may survive or may be present on other planetary bodies. All right, but going back to these regular glacial cycles, we have the Holocene being this most recent interglacial starting about 11.7 thousand years ago. I think it's important to note that within the Holocene, we have not been this steady interglacial period with no ice advances. There have been plenty of temperature variations within the Holocene, and that's what this chart is showing us here. We're looking at years before present, where present day is noted by this asterisk I just drew, and the mean temperatures are shown in black. So you can see how temperatures rose in the beginning of the Holocene, but since then have undergone some variations. And in fact, there's a dip back down that occurred recently in what's called the Little Ice Age. And before this, regionally, there were also other periods of time during the Holocene in which we had warming and cooling. I just want to note that the 2016 temperature is way up here. So when people talk about global warming just being a natural part of the interglacial periods that we're in and these natural cycles of climate, we can see that no, we're actually quite anomalous. The rise in temperature is unprecedented, and the temperature that we're currently at is much warmer than anything else during this interglacial so far. But this little ice age that we kind of started to come out of in the late 1800s was kind of interesting to note from a humanities perspective. On average, the world was about 1 degree Celsius colder. And we saw a lot of glaciers advance, and in the last 150 years since then have retreated quite significantly. Of course, that retreat in the last 50 years has really been exacerbated by climate change. But the Little Ice Age, since it existed during this time when cultures were flourishing across the world, is encoded in a lot of art. So for example, tourists vacationing in the Alps did a really great job recording what the glaciers used to look like in the mid-1800s, and we can compare that to what glaciers look like now. And this can be used to create chronologies of glacial retreat from the Little Ice Age. We tend to see in art more examples of people ice skating, particularly during the Little Ice Age, than we did in time periods before and after the Little Ice Age. And then we also have the infamous crossing of the Delaware by Washington and his troops in 1776, which is perhaps another example of the Little Ice Age, because nowadays we don't tend to see the Delaware being this ice-choked around in December. And so we think this might be another way in which Little Ice Age is kind of sneaking into our art and into our culture. All right, so now that we've gotten a little bit more familiar with the geologic timescale and with the current geologic epoch in which we live in, the Holocene, I'd like you to get a little bit more familiar with it. So please print, download, or bookmark the geologic timescale from the Geological Society of America, and then come up with a mnemonic device to remember the periods of the Paleozoic, Mesozoic, and Cenozoic. So for example, for the Cenozoic, I use "Please excuse Olivia, my perfect procrastinating horse," which corresponds to the Paleocene, Oligocene, Eocene, or Paleocene, Eocene, Oligocene, Miocene, Pliocene, Pleistocene, Holocene. And because there's so many that started with P, I use procrastinating for Pleistocene to remember the ST. Anyway, so have fun with that. And don't forget to watch the other lecture for today on geologic structures.